Hi everyone, thanks for joining the webinar today. My name's Alex Fowler, I'm a Principal Engineer with Arcadis, and I'll be presenting today on how we're using MIDAS and its integrations with other software to push beyond standard designs and standard practices. This is allowing us to deliver bridges that are more sustainable, easy to construct and install, and cheaper for our clients. So firstly, I'll be presenting an Arcadis bridge reconstruction project that we delivered a few years ago, and in that, with the help of MIDAS, we were able to give Network Rail as our client some of these benefits in a more kind of traditional, old-school project way. I'll then discuss how we brought these processes up to date on a current project with a sort of a digital upgrade, and that's through using MIDAS as part of a stack of software connections to identify and act on design and sustainability opportunities from the start of any project. This second project will cover the Network Rail range of standard bridge designs, and as we're probably all aware, we're currently in a market climate where we're focusing more and more towards that kind of standardization, and in particular focus on MVP, minimum viable product designs, but also trying to provide the most value for money on each project that we can, which can sometimes feel like goals that are in opposition to each other. And so I'm hoping that this presentation will give some examples about how products like MIDAS can help us achieve the best of both of those worlds. So the first project in today's presentation is a structure called Reservoir Road Underbridge. This is a bridge reconstruction project that we ran starting in 2016 and then came back to finish the detailed design stage of in 2020. The bridge is located in Whaley Bridge in the Peak District, and it sits on the branch line from Buxton into Manchester. Now, there are a couple of key constraints to the site to make the project more challenging. From the map view, you can see the first of the main constraints that the site imposes on the project, which is that the bridge is very close to the station in Whaley Bridge, and the end of the station platform actually runs right up to the back of the bridge abutment itself. Now, this means that there wasn't any room in the project for any realignment of the track, horizontally or vertically, if that was needed to fit the new structure into place. As we jump into street view, you can see the second main constraint, which is the limited clearance for the road beneath the bridge. The road itself is also on quite a steep slope, which puts a pinch point on the upper side of the bridge. And this meant that any new proposed design had to maintain, at worst, or improve on the clearance below the bridge while not making any change to the track level above. The original structure was completed in 1907, which made it over 100 years old by the time we started on this project, and it consisted of a single deck supporting both branch lines of the route. The original deck structure was formed of wrought-iron outer half-through girders, and then pairs of inner girders that formed troughs supporting the longitudinal track timbers. Between those, riveted steel deck plates connected each girder to form the remaining deck. You can also see from the section that the arrangement only provided a limited and non-segregated walkway in the cess, and that created a significant hazard for anyone like maintenance operatives that needed to cross the bridge to access the route. After more than 100 years of operation, the structure was reaching the end of its design life, and although previous assessments showed that most elements were in reasonable condition, issues with the future maintenance of the track timbers particularly meant that it would be more economical in the long term to replace the existing structure with a new bridge rather than to continue with ever-increasing maintenance costs and complexity with the original structure. The proposed design for replacement of the structure consisted of the single existing deck being replaced with two individual steel billet decks carrying one line each. Each deck had an external walkway which provided a full-width segregated crossing point for operatives, which removed that previous hazard from the existing bridge. For a bit of background, billet decks are kind of a structural form that have a thick steel plate forming the bridge deck between the inner and outer girders. And in this arrangement, the structural stiffness of the deck comes from the volume of steel in the deck rather than other arrangements where material might be more distributed and stiffness is provided through either cross girders and thinner steel plate sections or through a combination of composite steel and concrete arrangements. So the billet deck arrangement provides the benefit of reduced construction depth, which was crucial given the constraints of the site that I mentioned previously. But with that comes the design trade-off because the total weight of the structure is increased due to that high volume in the steel deck plate. So thanks to Google, we've got a nice before and after of the project, and you can see that the existing stone pilasters from the original structure have been removed to accommodate the new external walkways, and we've ended up with a new bridge that provides a new asset for Network Rail, extending the design life of the asset through the town and providing much easier maintenance as well as reducing hazards associated with the structure. You might be starting to wonder at this point why I've included this project as an example in the presentation. So while the project was a successful reconstruction project, and while there were a few constraints on the site that made the structure a little bit more challenging, it was, all in all, a pretty straightforward reconstruction project using a common structural type with standard design practices. Now, the reason I've used it as an example is due to an opportunity that the team had during detail design to take the structure beyond its standard basis and to provide a more efficient design. Following Network Rail design practice that's been in place for several decades, billet deck bridges like this one have typically been designed with deck plates of 125mm thickness for the range of spans that this bridge is within. However, during detail design, our MIDAS modelling highlighted that the deck plate was significantly underutilised at the standard 125mm thickness. Once that underutilisation was identified, several rounds of additional analysis were run with decreased thicknesses of deck plate until an appropriate utilisation of the deck was achieved. So firstly, a bit more about what that analysis looked like in MIDAS. We simplified the proposed billet deck into an equivalent beam plate FE mesh in MIDAS, using beam elements to model the inner and outer girders and plate elements to model the deck plate. Section offsets were then applied to shift the centroids of each component from the plane of the mesh to the correct position, ensuring the proper stiffness of the combined elements. Dead loads, including self-weight of the structure and superimposed loading from the walkway, ballast and tracks, were then applied to the model, as well as live loading from the walkways, thermal cases and braking and traction from rail vehicles. And then finally, moving load cases were modelled to capture the worst case positions of the standard LM71 model and Kirov crane vehicles that are included in MIDAS's vehicle library. So following the iteration of this model with decreasing deck thickness, our design team were able to confirm that a thickness of 100mm gave a higher but still acceptable utilisation without impacting the performance of the rest of the structure. So this opportunity amounted to a 20% reduction in the material required for the deck plate, which saved approximately 15.5 tonnes of steel across both bridge decks, and reducing the total lifting weight of each structure by 15%. Although carbon reporting wasn't part of project processes, kind of back in 2020, the steel reduction corresponded to a saving of approximately 30 tonnes of carbon from the design. Once we'd identified this opportunity for the cost and the weight savings, we then kind of took these back to our client, Network Rail, and coordinated with the contractor to confirm that the chosen section thickness was actually available. Luckily, both parties were happy to accept this design change, and this resulted in a cheaper project for Network Rail and an easier lift for the contractor, because they could reduce the capacity of their required machinery to kind of actually wheel and jack each deck into place. However, a lot of this was just down to good fortune on the project, really. The design team were lucky that they had enough time and budget left in the project to look more closely at the opportunity they'd identified. We were fortunate that Network Rail were happy to review and accept the change to an established kind of standard design practice, and we were also lucky that the contractor was happy to take it away and coordinate with their supply chain to accommodate the change that had been made to the previous design. And if any of those single pieces hadn't fallen into place, the simplest thing for the project to progress would simply have been to ignore the opportunity that had been identified and to deliver a bridge with the thicker 125mm deck plate and simply accept the fact that there was over-design in the structure. So the question is really, how do we make sure that we can get outcomes like this more often without having to rely on that kind of good fortune and project luck? How do we identify design opportunities like this more often so that we can continue to kind of optimize designs and provide as much value for money as possible. And how do we change our processes so that we make sure that we're not missing that kind of design opportunity for improvement by just accepting standard practices like the 125mm deck plate thickness. Any good engineer wants to deliver a structure with as little over-design in it as possible, not only to save their clients money, not only because it's technically rewarding to make something work better than previously, but also because we have an obligation as civil engineers to be as sustainable as possible in our designs. And so in the next section, I'll present one of the ways we're looking to try and kind of answer all of those questions and make that happen. So as I said in my introduction, there is a conflict between kind of two competing market forces at the moment, which is the push to standardization by clients in order to save money, and the need for companies, engineering consultancies, who are competing with each other in the marketplace to maximize value for money for those clients. Now, the chart on this slide may be familiar to those of you who have kind of had some brushes with our commercial and project management colleagues. And it essentially shows how the potential cost savings that can be made as you take advantage of changes and opportunities drops off drastically as you progress through each stage of a project. So by the time the design team on Reservoir Road Underbridge, for example, identified that they could save on the deck plate thickness, the project was already at the detailed design stage, that red arrow, and had already spent a decent portion of the project time and budget designing a bridge with the thicker 125mm deck plate. So additional project time was needed to reanalyze the bridge with a thinner deck, which fortunately could be done within the project budget, but still cost additional time and money, and so cancelled out some of the benefits that were achieved. Now, in line with the curve on this chart, if we could identify and implement opportunities earlier in the project, then we could have a much greater benefit for the project than at that final later design stage. In the earlier project stages, we usually have far less time to make this happen with less budget available, and we'd typically normally only develop kind of high-level concept designs. And these would be done manually to a lower level of detail, typically using rules of thumb and previous projects as the starting point for our options. It's very rare that anyone's kind of putting together a complicated MIDAS model at the optioneering stage of a project. So one way forward to deal with this challenge is to use digital tools and processes like MIDAS to automate that process of identifying design opportunities at the earliest possible stage. So if the engineering team can identify inefficiencies in a standard concept design or within standard design practices at the project outset, they can offer an optimized design from the outset of the project. And this offers increased certainty to all parties involved. The designer has more confidence that they're putting forward a design that they'll not be reanalyzing and redesigning later on. The contractor can take that design and engage with their supply chain earlier and reduce the risk of at a later stage not being able to accommodate design changes. And the client throughout the project then will have fewer technical changes to review and consider. And in the next section, I'll be running through how we've kind of acted on this approach and put it into practice within Arcadis. So we decided that if we were going to start identifying design opportunities for standard aspects of railway bridges, there was no more obvious place to start than the Network Rail Standard Design Suite. These designs are a set of standard design documents and drawings that Network Rail have produced over the years for a range of different overbridge and underbridge applications, usually identified by a letter or an acronym such as the U-type or the E-type underbridges that are kind of shown on the slide. The designs for each bridge type consist of different structural arrangements with predefined sections and details for different design scenarios. So those would be kind of acceptable ranges of span, skew angle, construction depth from rail, and applied loading. And that's all specified for the range of arrangements covered by the standard design. The sections and design details for kind of each standard arrangement can then simply be read off the design tables produced by Network Rail and submitted by the designer. And the idea of this is that a project can be delivered far more quickly if a proposed design stays within the parameters of the standard design, such as span, skew, and construction depth. And if that's the case, then the designer's not required to kind of submit any detailed calculations or any kind of analysis as part of the deliverables, because that's already covered by the design standards. However, the flip side of that advantage is that because of the high degree of standardization, there will inevitably be inefficiencies and over-design if your bridge doesn't sit towards the top kind of most extreme end of each design range. So for example, I've shown one of the design tables for a standard U-type bridge deck. And to use this table, basically, once you have your required span and skew for a particular site location, you basically read down the table and you can simply read off all the details for the standard girder section design from the row within the next span increment. So for example, if your bridge is somewhere between 12 and 14 metres in span, you apply the section details for the row of the 14 metre span. However, from that, you can kind of see almost immediately that if you were to have a design scenario where your bridge has a span of 12.1 metres and it sits perfectly square to its abutments, it's definitely going to be over-designed if you're then picking out a standard design that covers all designs up to 14 metres span and 25 or 50 degrees of skew. We're currently running this process to identify design opportunities and to improve project certainty from the outset on a project we're doing in North East London. The project consists of 3 parallel bridge replacements on the London Overground network, and the initial proposal for these 3 bridges was to replace the original single deck structure at each location with a pair of standard U-type decks, so a total of 6 decks across the whole project. You can see on the map that these 3 locations sit across a large curved section of the overground route, and this means that each new pair of bridges has to be completely different from each of the other pairs in terms of both span and skew arrangements. And what that means is we're essentially running 3 design projects at once, but unfortunately not with the program time or budget for 3 separate design projects. Now looking at the most skewed structure from Street View, an additional aspect of this project is that each of the bridge locations has an area of Network Rail owned land, which is the red highlighted areas, directly in front of the existing abutments, which will be used to construct a new abutment on each side to reduce the span of the new bridge decks. However, because this area is currently open and accessible to the public, kind of directly adjacent to the pavement and footpath, Network Rail want to minimise the extent of land that needs to be kind of used for the new abutment structures in order to reduce the impact of the project on the local community. So the first step we've developed to make our kind of design process for this project more efficient is to develop an automated optioneering and setting out tool for the kind of the earliest optioneering stage of the project. This tool uses design software called Grasshopper, which is a visual programming add-on to the 3D CAD modelling software Rhino. If any of you aren't familiar with that, but are users of AutoCAD or MicroStation, you may have come across the Dynamo or generative component add-ins for those packages respectively, and those basically do the same thing. As a quick explainer on what visual programming is, it's software that allows you to provide a set of inputs, compile a set of processes to do something with those inputs, and then throw out the final results. But it comes without the complicated step of having to learn any coding languages to carry out those functions. It's called visual programming because all of the processing for a particular function has been bundled into nice, simple visual boxes, and all the user needs to do is to simply connect the outputs from one box, one function, to the inputs of the next step in the process. So for the example on the screen, I've simply specified 2 sets of coordinates in the left-hand yellow boxes, just as numbers, and then you can follow the black lines from those to see how those coordinates can create a pair of points with one function box, and then from those point functions connect to make a line. Now that line is created in 3D CAD space, and I can also then kind of read the length of the line as a separate output if I ever need to use that for a different process. Now, if I need to go back and change the position of one of the points, I can simply go all the way back to the left-hand side, change one of the values in the yellow boxes, and the whole process of wires and boxes simply reruns automatically. So for our optioneering tool, we can input the site geometry from basic topo survey information for a particular site, and the automated process then generates a detailed model of different deck types, different structural forms that will fit around the rail gauging profiles from the existing track strings, and also fit within the geometry constraints of the site. Now, this allows us to rapidly identify if there are any clashes between a pair of decks in kind of the different proposed structural forms, and fine-tune their positions to try and make them fit together. So, for example, you can see the red and green decks with daylight between their inner girders, which was a result of us kind of fine-tuning the position of the deck centre lines away from each other underneath the fixed track positions. The benefit of this tool is that it also highlights if a bridge has to go beyond the range of the standard design parameters in order to work, in which case we know from the outset that we would have to carry out a bespoke design development later on in the project. Now, all of the information this tool gives us allows us to quickly determine which structural types can and can't be used at a particular site, and to rule them immediately out of option developments at a later stage, saving us valuable project time. Now, because the tool does all of this very quickly, automatically, we've been able to iterate through a number of potential new abutment positions on the Network Rail-owned land at each location. The setting out checks that are included and run automatically within the tool would be really time consuming if we had to do them over and over again by hand to try and find the best abutment position. So the tool's given us a big advantage in being able to reliably say how much land take there will need to be at a particular location. I mentioned the curvature of the track alignment for all three structures before, and this space-proofing exercise quickly identified that the original proposals for a pair of replacement U-type decks wouldn't work at the worst-case location. The curvature of the deck was simply too great, and it meant that the proposed decks would have to be too wide, and that the internal girders between the pair of decks would clash in a way that couldn't be avoided by shifting the positions of either deck. Now, this meant that the design team were able to switch their proposed concept design to a different type of standard design instead, and quickly confirmed that this wouldn't suffer from the same space-proofing issues. Having that information confirmed so early on by the tool meant that we were able to avoid progressing any further with a concept design that was destined not to work, without wasting any time carrying out design checks or kind of early design work. So the second step in this process is to then link the 3D geometry of the concept design to a MIDAS analysis model. This is done using the plugin that MIDAS have developed to create a connection between the Grasshopper and MIDAS software programs. So once we're happy with our deck geometry, its position and its clearances, both to the rail and to the road below, we can run the connection from Grasshopper to MIDAS to automatically generate our analysis model. We can follow similar logic to the FE analysis we did for Reservoir Road, simplifying the proposed structure down from a 3D model to equivalent elements with geometry, specified material, and section properties. However, now all of those steps can be done automatically within the MIDAS plugin based on the input geometry. The mesh of nodes and elements will set out to whatever orientation and dimensions are required by the input geometry, and materials and section properties can be specified by the engineer with just a few clicks. Now, I'll put some simplified examples on the screen of how MIDAS has provided those steps bundled into self-contained boxes to make things easier for the user. Each step of producing analysis manually is replicated and can then simply be joined together to produce one complete process. The main gain that the MIDAS plugin gives us is that once a process for generating a model of a particular structure type, so for example in this case the U-type, once that's written, it can be used for any arrangement of that same bridge type. The plugin runs and it follows the same rules and logic each time. So when you change the inputs, you can change the mesh or anything else in the model automatically. Just as for the geometry, the load cases and combinations are also automatically generated within our tool, so that basically a full analysis is ready to run with just a few clicks. Our tool is set up to read in the geometry of the track over the bridge, so that any vehicular effects are captured and calculated automatically, such as the kind of the position of the track and any cant and curvature that may add additional effects. Now, MIDAS have developed their plugin to have a two-way connection with Grasshopper, so that also means that once the analysis is run, the results can be fed directly back into our tool to highlight areas for potential optimization. The inputs to the tool can also be manually fine-tuned so that we can then rapidly check whether optimizing certain sections will still produce a passing design with acceptable utilization. So, with all of that said and done, the question on everyone's minds may well be, why bother with all of this? Why go to all this effort and bring in all of these bits of software together when a standard answer, a standard design, can simply be picked straight off a drawing? It's all well and good, but isn't it just easy for everyone to stick with the answers that have already been come up with? The truthful answer is that sometimes the standard design will be the right one. There may not be much over-design to remove from a particular arrangement, and even if there is, there just might not be enough benefit to a project to justify the cost and the time of doing that extra work. But now that we can use MIDAS and its connections to programs, other design tools, other software packages, we're in a position where we can get the answers to those questions with just the click of a few buttons once an automated process has been developed. And that allows us to get the best of both worlds, really. We can identify opportunities to optimize the starting point, the standard design, and really quickly be able to put a solid number with a lot of confidence on what the costs and the benefits will be of doing that extra work. And if those benefits are sufficient enough, we can make those changes early on enough in a project that we don't waste time later on in the project and avoid any nasty surprises. Ultimately, we now know that we can get to the end of a project and know that we've provided our client with the right answer, not always from a technical perspective by squeezing every single bit of capacity out of every component on the bridge, but by knowing that our design is the best value for money that is possible to achieve on the project. So that brings us to the end for today. I hope you found this presentation interesting, and maybe the next time you pick up a standard design or come across a bit of good practice, there'll be a chance to push it further. Thanks very much.